Welcome to chemistry class with your teacher, Anakwe Christopher GK. In this video, we'll be looking at the topic titled Mass-Volume Relationships in Chemical Reaction. Mass-volume relationships in chemical reactions. In the chemical reactions, you do see, we want to look at the mass and volume relationships that are in chemical equations. All right, it's expected by the end of the end of this video, you should have learned what stoichiometry is, about reactions and calculations that involve gas volumes. The next thing we will talk on it as a course content is standard temperature and pressure. So we are going to look at these key three things and learn about them. So we are going to take them one after the other. First of all, what stoichiometry is and the reactions that has to do with mass volume relationship, or the calculations that involve mass and volume relationships. All right. First of all, we need to understand that a balanced chemical equation of a chemical reaction tells us the relationship between quantity of the reactants and one another. And another is the product that is being formed. Now listen once again. Chemical equation tells us about the relationship between the quantity of the reactant to another reactant that comes together to form a product. It tells us about the relationship between the amount of the reactants and the products, and that is being known as stoichiometry of a reaction. That relationship between the amount of the reactant and the products, that is the reactant that forms the reacts to form a product, the reactant. So the relationship between the two is what we call the stoichiometry of a reaction. The amount of the substance that reacts that forms so amount of substance. Such relationship is what we call what? Stoichiometry. So stoichiometry is what? Is therefore the study of the quantitative relationship between mass and volumes of the reactant and product in a chemical reaction. Stoichiometry is the study of the quantitative relationship between mass and volumes of a reactant, and the product or the products in a chemical reaction. So stoichiometry is ordinary chemical arithmetics. Simple. All right. Now, in that chemical equation, we have what we call mole. In any given chemical equation, we have what we call mole. What is mole? Mole is the amount of substance containing Avogadro's number of that formula unit. So it is the amount of substance which contains as many formula units as the atoms in 12 grams of carbon-12. We know that amount in carbon-12 of a carbon-12 is made up of one mole, and 1 mole is the number of Avogadro, which numbers 6.02 times 10 to the power of 23 atoms or ions or molecules, as the case may be, or particles generally. So the numerical coefficient of a balanced equation represents the number of moles of the reactants and products. When a chemical equation is given, you will see a coefficient. It will be either written 2 or 3 or 4 or 5 or 6, as the case may be. One is being neglected because it's not being written, meaning that a symbol or that particular element or compound there, without putting anything, shows that it's one mole of it. So we don't normally write 1, but it tells you the number of mole of that particular equation or element. All right, mole ratio. What is now the mole ratio? Mole ratio is the numerical ratio of combination between the reactant and the product of a balanced chemical equation. What it just means, it just the moles. You now ratio it is to. You put the sign of is to in the ratio of the moles there. So for instance, the following balanced equation, you see number of mole of magnesium is 1. That is why 1 is not written there, but it's telling you that magnesium is 1 there. Then that of the hydrochloric in aqueous solution, hydrogen chloride aqueous, is 2 mole. You see 2 in front of hydrogen chloride magnesium chloride is 1 because one is only one magnesium chloride is there. That is why we have 1 there. We don't write that 1 because it's 1. So the same thing to hydrogen gas. Then that is the mole. The mole ratio now is 1:2:1:1. That is the mole ratio. So as long as you have the mole, you have already gotten the mole ratio. Just put it in between the reactant and the product. Okay. So the stoichiometry of the above reaction, of the above reaction or chemical equation, can be expressed that 1 mole of magnesium reacts with 2 moles of hydrochloric acid, and it produces 1 mole of magnesium chloride and 1 mole of hydrogen gas. That is the stoichiometry of that particular reaction. It tells you how many mole of this that react with how many moles of the other one to produce how many mole of this and that. Whereas the mole ratio of the combination of the reactant and product is 1:2:1:2. I've said it before, just putting is to in the mole ratios, in the mole, give you the mole ratios. Okay. The reactants and the products in the chemical reactions may be ions. They may be atoms or they may be molecules. But nevertheless, the number of moles involved in the reactant is not affected by the kind of particles present. The number of moles is not affected if it is ion, if it is atom, if it is molecule. No, it's not being affected by that. So since a mole represents the molar mass of the substance in gram, we can also evaluate the reacting particles, reacting mass relationship between the reactant and product from a balanced equation. So the number of mole is not being affected. For that, we can evaluate the reacting mass relationship between the reactant and the product. So whether it's ion, it is atom, or it is molecule, is not being affected. So we can evaluate that. So let's take some example of an equation. We brought out this one before. The magnesium reacts with hydrochloric acid or hydrogen chloride aqueous, which is hydrochloric acid, to produce magnesium chloride and hydrogen gas. All right, number of mole is 1 mole is to 1 mole, 2 mole, 1 mole, 1 mole, 1 mole. The mole ratio 1:1, 1:2:1:1. Then molar mass now is the relative atomic mass of magnesium. Then that of the hydrogen chloride is chlorine time plus that of the hydrogen. It gives you that magnesium chloride, you add up the molar mass. Then the same, where this molar mass of each of them is the same thing as their reacting masses. Their reacting masses is just that molar mass in gram. You gram it. Now times the number of mole in front, that is the number of mole in front of each of the equation or the formula given. Now look at the molar mass. That of the magnesium is 24, and the reacting mass is 24 because it's 1 mole. For that of the hydrochloric acid, the molar mass is 36.5. That is the molar mass, but the reacting mass is 2 times that because it is 2 mole of hydrochloric acid that react with magnesium. So the same thing affects the others. The only one that is this 1 mole, the same thing as the number of mole and that of the number of reacting mass. But any other one that has bigger mole than 1 times it with the molar mass, it will give you the reacting mass. Okay, from the above data, we can see that the number of mole times molar mass gives you the reacting mass. Simple. If that is the case, we can now say make the number of mole the subject of formula. You are going to have reacting mass all over molar mass. So mass all over molar mass is the same, is the formula to find the number of mole. So if the reacting mass or the number of moles of any of the substance in the reacting equation or in the equation is given, we can calculate the reacting mass or masses or the number of moles of the other and from the balanced chemical equation. We need to know that this is the equation for that, equation for the reaction. Okay, so let's take some example. Calculate the number of moles of calcium chloride that can be obtained from 25 grams of limestone in the presence of excess hydrogen chloride. The relative atomic masses of the elements we are given, and the equation for the reaction is this. Calcium carbonate plus hydrochloric acid produce calcium chloride, water, and carbon dioxide. We are asked to find the number of mole of calcium chloride that is being formed, that is being obtained from calcium carbonate, which is limestone. So with that, we are going to solve it this way. From the equation, we observe that 1 mole of calcium carbonate, which is limestone, produce 1 mole of calcium chloride. Now, with the equation given, which is the reacting mass all over molar mass, 25 grams of what? Calcium carbonate all over what? 100 grams of that calcium carbonate. You are going to have the number of mole, which is 0.25 mole of calcium carbonate, which is limestone, calcium triosocarbonate 4, which is 0.25 mole. Therefore, 0.25 mole of calcium carbonate yields the same mole of calcium chloride, because 1 mole of calcium chloride was produced by 1 mole of calcium carbonate. So that is how to calculate that, because the same mole, 1:1. All right, second example is this. What mass of lead 2 triosonitrate 5 will be prepared to yield 9 gram of lead 2 chloride on the addition of excess sodium chloride solution? We can see the equation for the reaction. 1 mole of lead nitrate produce 1 mole of lead chloride, and we are asked to find the mass. This time around is mass, not the mole. We are asked to find is the mass of lead triosonitrate. This that will be required to yield this. All right. From that, we found out that 1 mole of lead nitrate required 2 mole of sodium chloride, and 1 mole of lead chloride was produced, and sodium nitrate 2 moles. Now you are going to just from there you find the molar masses of lead nitrate, sodium chloride, and lead chloride, and the sodium nitrate. When you do that, to find the molar mass, and from that, the above data, we can see that 278 grams of lead chloride are obtained from 331 grams of lead nitrate. If that is the case, how many of lead nitrate will be obtained from 9 grams of lead chloride that was given in the equation? You just need to cross multiply 9 times 331 all over 278. When you do so, you multiply and divide, and you have 10.7 grams of lead nitrate will be obtained. So it's very, very easy based on the equation for the reaction. Once you get the equation for the reaction correctly, and it's been given to you already, so use that and you get your answer correctly. Okay, so let's take the third question. Determine the mass of carbon 4 oxide produced on burning 104 grams of ethane. 104 grams of ethane. For burning this ethane, we're asked to find the number of carbon 4 oxide, the mass of carbon 4 oxide that will be produced by burning ethane. Equation for the reaction is being given. As long as the equation for the reaction is being given, it's easy. The same thing we just did now, we are going to do it. Find the mole ratios, find the mole, 2:5:4:2. Then with that, bring out the molar masses and find the solution. Now, mole is mole, 2:5:4:2. Their molar masses 26, 32, 44, 18, based on the equation for the reaction. Now, the amount to find the mole, the amount that reacted, mass, not mole, amount now is in mole, mass of ethane all over molar mass of ethane. With that, you do it and you find this mole. And from the equation, 2 mole of ethane produce 4 mole of carbon 4 oxide. If that is the case, this 4 mole of ethane now will react to produce what? Cross multiply this 4 times this particular 4 divided by this 2 will give you 8 moles. If 4 mole of ethane reacted here, it means that 8 mole of carbon 4 oxide will be produced. Hence, the reacting mass of carbon 4 oxide will then be number of reacting mass reacting mole of carbon dioxide times the molar mass. If you do so, you multiply. So 8 mole of carbon dioxide times the reacting mass, it will give you 352 grams per mole, which is the number of molar mass. This means that 352 grams of carbon dioxide are produced by burning 0.14 grams of ethyne, based on the equation for the reaction, or equation given to us. So that is it. And reactions involving gas volumes. We have some things that reaction that has to do with gas volume this time around, not longer gas gas and number of mass only, but this one now is gas volume. We have talked about the mass. We want to talk about the volume. Here is where a man called Gay-Lussac did a wonderful work to us. Now, equal volumes of gases at a given temperature and pressure contain the same number of mole. We can calculate the volume of gases from a balanced chemical equation, provided that the gases are under the same condition of temperature and pressure. The coefficients of the gases, of gaseous reactant and products in the balanced equation give the mole ratio or mole relation, as well as the mole relation among the gases. So just like the way we did before, ammonia reacts with oxygen to form Dix, and we see 4 mole, 5 mole, 4 mole, 6 mole, and the reacting volume is just the way we have the mole ratio is now the reacting volume. Instead of mole, you use the volume. 4 volume, 5 volumes, 4 volume, 6 volume. All right, we are going to, from this particular reaction we understand that from that particular, that we have 4 volumes of ammonia react with 5 volumes of oxygen to yield 4 volumes of nitrogen 2 oxide and 6 volumes of water vapor. And we can record that 1 mole of any gas at STP occupies what? 22.4 dm cube. That is at STP. Thus, we can calculate the volumes, masses, moles, and the number of molecules of gaseous reactant and product from a balanced chemical equation, as long as the equation has already been written. Okay, let's take an example. In the industrial preparation of hydrogen triosochlorate, hydrogen triosonitrate 5, triosonitrate 5, ammonia used is born in oxygen in the presence of a catalyst according to the following equation. Look at the equation. What is unique to, you are interested in this kind of calculation, is the equation for the reaction. So in this equation for the reaction, you are asked that 260 cm cube of ammonia are burned completely. What is the volume of oxygen? Volume of oxygen, this oxygen used up, and the volume of NO, nitrogen 4 oxide, or nitrogen 4 oxide, that is produced, Dix and Dix, or nitrogen 2 oxide, sorry, nitrogen 2 oxide you produced. You just need to compare the equation for the reaction. The mole, the volume, mole volume, 4:5:4. So the one that is produced, compare the volume. All right, with that, we are going to see from the equation for the reaction once again, 5:4:5:4:6. We need to divide through with the mole ratio of that of the ammonia. And when you do so, you're going to have 1:1.25:1:1.5. Therefore, the volume, the first question says the volume of oxygen used up. 260 cm cube of ammonia we use up what? 5 times 4 times 360 cm cube of oxygen. When you do so, you're going to have this 4/5. 4/5 is this thing that we divided. Is 5 divided by 4, the volume of ammonia we divided. You have this. Then the volume of nitrogen 2 oxide produced, if you divide it, it's going to give you the same number of ammonia that was used, because it's the same volume volume of nitrogen used that was also produced in that of the nitrogen 2 oxide. So it will give you the same. That is how to do that. Another question, 20 volume of carbon 2 oxide was mixed and sparked with 200 cm cube of air containing 21% of oxygen. If all the volumes are measured at STP, calculate the total volume of the reacting gases. All right, we are going to start this by first of all knowing that 200 cm cube of air means that oxygen contains 21%. That means 21 divided by 100 times 200 all over 1. And you are going to have 42 cm cube volume of oxygen there. Meaning that nitrogen will now be 200 minus this minus 42. It will give you the volume of nitrogen because oxygen does not contain only, air does not contain only oxygen, but nitrogen is also there. All right, we are going to bring the equation for the reaction. And with that, you see the mole ratio 2:1:2. Before sparking, it means that the volume was given 20 cm cube of carbon 2 oxide, 42 cm cube of oxygen, and 0 before sparking, that of the carbon 4 oxide, because before sparking. Then one is now in reacting volume now will be 2. Since it's 2 of these, 2 of carbon 2 oxide give 1 of these. That means 20 of carbon 4 oxide, carbon 2 oxide will need half of itself. That means 10 of oxygen, meaning that after sparking, oxygen is going to have 32 left, of course, based on the equation for the reaction, and what we will have after sparking in the carbon 4 oxide is 20. Then therefore the volume of the reacting gases will be 32 plus 20 plus 158. This 158 volume of the nitrogen, and all together is going to be 210 cm cube. Okay, the third question will be calculate the volume of carbon 4 oxide at 27 degrees Celsius and the 750 millimeter mercury, which could be obtained by heating 10 grams of limestone. The molar mass of limestone was given, carbon 4 oxide was also given, and the molar volume of gas at STP was also provided to you as a constant, of course. With that, bring out the given equation and they take their mole ratio 1:1:1 in the mole ratio, and with that find the number of mole, that amount of carbon 4 amount of calcium carbonate, which is reacting mass all over molar mass, and you're going to have the number of mole 0.1 mole. If that is the case, it means that 0.1 mole of calcium carbonate will yield 1 mole of carbon 4 oxide. And at STP, 1 mole of any gas, including carbon 4 oxide, occupies 22.4 dm cube. That means 1 mole of carbon 4 oxide occupies 22.4 dm cube. All right. If that is the case, we have gotten that one, the volume now, using the general gas law, P1 V1 all over T1, P2 V2 all over T2. Bring out the given the value given. If you use that, you are going to find the V2, and in finding V2, you are going to have final answer. When you substitute correctly, you are going to have V2 as 2,494 cm cube. 2,494 cm cube as the V2 volume of carbon 4 oxide liberated. All right, that is a good one, and we know that the V1 is what we found before. Then when you convert this one, when you convert it to dm cube, we are going to have 2.4 dm cube, 2.4 dm cube, because this one is in dm cube. The V1 is going to be 2.4 dm cube. All right, in terms of standard temperature and pressure, before we conclude this particular video, we need to understand the volume of gases changes remarkably based on changes in temperature and pressure. We need to understand that. Why is this so? Two chemists could be, one could be in England, another one could be in Nigeria. in carrying out a particular practical, identical investigation on gases. But their gas volume will differ remarkably because of the temperature, difference in temperature between the two countries. For that reason, scientists therefore decided that 0 degree or 273 Kelvin will be standard temperature. Because of difference in temperature in different countries, scientists now decide that 0 degree Celsius or 273 Kelvin will now be standard temperature, and 760 millimeter mercury or 1.01 times 10 raised to the power of 5 Newton meter square or 1 atmosphere will be the standard pressure at which gas volume are given. So standard pressure and the standard temperature are being given because of difference in temperature in different countries and where experiments are being done. So these values are being used as standard temperature and pressure. And the molar volume of gas at STP is being taken as 2.4 dm3. And that is what we mean by standard temperature and pressure. And it came about because of the difference in temperature and pressure in different countries and regions. Okay, and we have units of measurements, which we call SI units. SI units simply means international units, international system units. And it is the language used by scientists to measure units. And several things have several units. And as you can see in the chart, you need to look at it critically and learn them. And with that will end our class for today. And for further discussion and inquiry, do well to get to me through my phone line +23480 655 or at crystal116@gmail.com. That is my email address in case you want to send me an email. Thank you for being part of this particular class and remain blessed. Thank you and get ready for the next video.